This video lecture will discuss the operation of resistors. Resistors are the simplest components that can be used in a circuit. Simplest in the sense that the relationship between the voltage across a resistor and the current flowing through it is a proportionality relation, as we will see. The symbol used for a resistor is this one. A resistor features a characteristic parameter called the resistance, typically indicated with the letter R. If a current I flows through the resistor and a voltage V is placed across the resistor, then the relationship between the voltage V and the current I is provided by the so-called Ohm's law. In particular, Ohm's law says that in this resistor, V is equal to R times the current I. So the resistance R is the proportionality factor between the voltage across the resistor and the current flowing through it. The arrow we use to indicate the voltage points to the end of the resistor conventionally placed at the higher potential. According to Ohm's law, the voltage V has the same sign as the current I if the current enters the resistor from the node at the higher potential. This is also in agreement with the so-called passive sign convention, which we will meet again later on during these video lectures. If the current entered the resistor from the node at a lower potential, then the voltage and the current would have opposite signs. Of course, if a current flows into a resistor from one end, then the same current will flow out of the same resistor at the other end. The unit of measurement of the resistance is the ohm, indicated with the Greek capital letter omega. Typical values of resistances in an electronic circuit go from the ohm to the kilo ohm, which is 10 to the third ohm. The prefix K stands for kilo, to 1 mega ohm, which is 10 to the 6th ohm. The prefix M is for mega, to 1 giga ohm, which is 10 to the 9 ohm. The prefix G stands for giga. We might now wonder what is the origin of Ohm's law, and in particular, how the current flowing through a conductor depends on the applied field and on the characteristic parameters of the material. First of all, let's see what happens to an electric charge Q in vacuum when an electric field E is applied. What happens is that the field exerts a force F on the charge, and this force is equal to the mass of the charge times the acceleration. So the field will accelerate the charge proportional to the applied force. The applied force can be expressed in terms of the field and the charge as E, the field, times the charge Q. From this equation, we get that the acceleration of the charge carrier, A, is given by the field times the charge divided by the charge carrier mass. This is the case of a charge carrier moving in vacuum. It is reasonable to expect that the behavior of the same charge carrier in a conductor will be different as compared to the case of the motion in vacuum. Now, a metal features a uniform structure consisting of elementary cells with a given regular shape, repeating themselves with some spatial periodicity. The lattice, the reticle shown here, is meant to represent the metal structure in a very simplified way. Of course, the structure of a real metal extends in the 3 dimensions. In a metal wire, the acceleration of a charge under the effect of an electric field is slowed down by the very structure of the metal itself. So, under the effects of a field, applied to the metal wire, a charge will start accelerating and will abruptly stop when it collides with one atom in the lattice. Then again, under the action of the electric field, the charge will start accelerating again until it interacts with the next atom in the lattice. At that time, the charge will stop again, and then, under the action of the electric field, will start accelerating for some time, and so on and so forth. The length of the path along which the carrier is accelerated is related with the periodicity of the crystalline structure of the metal, but actually changes every time because the lattice vertices, which are the atoms at the vertices of the crystalline structure of the metal, oscillate about their average position. It is in a way possible to define an average length of the interval along which the carrier is accelerated, and this average length is called the mean free path. Therefore, the speed of a charge carrier moving through a metal wire under the action of a field is never constant. It starts increasing from 0, then it goes back to 0 abruptly when the charge carrier interacts with the atoms of the crystalline reticle of the metal, and then starts increasing again under the action of the electric field. It's anyway possible to define an average speed for the carrier, and this average speed v sub d is called drift velocity. And this drift velocity is proportional to the electric field through a parameter mu, which is called the mobility of the carrier. Mobility is a characteristic feature of the material we are considering, so of the metal making up the wire, and also is a function of the temperature. In particular, the mobility tends to decrease when the temperature increases. So while for a charge carrier in vacuum, the acceleration is proportional to the applied electric field, in the case of a charge carrier in a metal wire, the speed is proportional to the electric field. Let us consider now a metal wire with a section with area A and free charge density N sub m. The wire is under the action of an electric field. We know by now that the charge carriers in the metal wire under the action of the electric field will move with an average speed with a drift velocity, as we defined it, Vd equal mobility mu times the electric field. We wonder now how much charge delta Q passes through the section A in a time delta t. This charge will be all the charge in the small cylinder with base area A and height given by the drift velocity Vd times the time delta t. So delta Q is the charge in the shaded volume in the metal wire. So the charge delta Q is given by the volume of the small cylinder, which is the base area A times the drift velocity times delta t times the free charge carrier concentration N sub m times the charge carried by each individual charge carrier, let's say Q. Now, by definition, the current flowing through the wire, the current I, is given by the ratio of the amount of charge delta Q passing through the section A in a time delta t and the time delta t. So based on the expression we got for delta Q, the current I will be given by A times the drift velocity Vd times the carrier concentration times the charge Q. Now we can replace the expression of the drift velocity as a function of the electric field, and what we get is the area A of the section of the wire times the mobility mu times the electric field times again the carrier concentration times the elementary charge Q. Let us define now the current density J as the ratio of the current I and the section area A. Based on the expression we wrote above for the current density, as we defined it, will be given by the mobility mu times the charge carrier density N sub m times the elementary charge Q times the electric field E. This same expression can be rewritten in a shorter form as sigma times the electric field E. Now, J equal to sigma E is nothing else than Ohm's law. Sigma equal to the mobility times the carrier concentration times the elementary charge is called the conductivity of the metal. Sigma, the conductivity, is a characteristic parameter of the material we're considering. Apart from Q, which is a universal constant, mu, the mobility, depends on the metal we are using, and also the concentration of free carriers, and sub m depends on the material that makes up the wire. We already know that Q, the elementary charge, is approximately given by 1.6 times 10 to the minus 19 Coulomb. The Ohm's law in the form that we have just obtained, written as current density equal to conductivity times the electric field, can be rewritten as E, the electric field, equal to the current density divided by the conductivity. This equation can also be written as rho times the current density, where rho is the resistivity, which by definition is given by 1 over the conductivity, or 1 over the mobility times the carrier concentration and sub m times the elementary charge. As for the conductivity, also the resistivity is a characteristic parameter of the material making up the wire. The unit of measurement of the resistivity is the ohm per meter. Of course, the unit of measurement of the conductivity will be ohm to the minus 1 times meter to the minus 1, or Siemens over meter. S stands for Siemens. Of course, 1 Siemens is equal to 1 ohm to the minus 1. Some examples of resistivity in different materials, for example, the resistivity of aluminum is equal to 2.8 times 10 to the minus 8 ohm per meter. The resistivity in copper is equal to 1.7 times 10 to the minus 8 ohm per meter. The resistivity in gold is equal to 2.4 times 10 to the minus 8 ohm per meter. And the resistivity in silicon, which by the way is not a metal like aluminum, copper, and gold, but is a semiconductor, is equal to 6.4 times 10 to the second power ohm per meter. As you can see, the resistivity in silicon is much, much larger than the resistivity in metals. Let us consider again a metal wire featuring a length L and some charge density. This wire is assumed to be under the action of an electric field, E, and under the action of this electric field, the charge carriers will move in the direction indicated by the field. Okay, here we are assuming the convention that the charge carriers carry a positive charge. We know that the electric field E is connected to the potential by the relationship E equal to minus the derivative of the potential, let me call it V prime, with respect to space. If the electric field is uniform here, then this same expression can be written as minus V prime divided by the length of the wire L. The minus sign in this expression tells us that the potential increasing going backwards along the field lines. From this expression, we get that the potential can be written as minus the length of the wire times the electric field. It is intended here that the positive direction of the potential is the one defined by the electric field. If we define the potential as pointing in opposite direction as compared to the field, then we can rewrite the last expression as V equal to minus V prime equal to the length times the electric field. From the last equation, we can write again E as the potential V divided by the length of the wire L, but we know also that E is the resistivity times the current density, or the resistivity times the current divided the area of the section of the wire. From this last equation, we can now get the voltage V as the resistivity times the length of the wire divided by the area of the section of the wire times the current. This is the form of the Ohm's law as we first stated it. Okay, so we can rewrite this last expression as the resistance times the current, where the resistance is given by the resistivity times the length of the wire divided by the area of the section of the wire. Let me rewrite here the last equation expressing the Ohm's law as the voltage equal to the resistivity times the length of the wire divided by the section area of the wire times the current, or the resistance times the current, where the resistance is rho times the length of the wire divided by the section area of the wire. From this last expression, what we get is that if we want to increase the resistance of a metal wire, we have to increase the length of the wire or reduce the area of its section. Actually, one way to fabricate a real resistor is by using a very long and thin metal wire. The Ohm's law can be written in a different form as I, the current, equal to the voltage divided by the resistance, or G, the conductance, times the voltage. Of course, the conductance G is the reciprocal of the resistance and is measured in Siemens. The conductance can also be measured in ohm to the minus 1 or reverse ohm, also called mho. Power dissipation in a resistor can be calculated as P equal V times E according to the well-known definition. We can replace I with its expression based on the Ohm's law, and what we get is V over R, and eventually V squared over R. Or again, in the expression of the power V times I, we can replace V with its expression based on Ohm's law, and what we get is I times R times I, which gives us I squared times R. So the power consumed in a resistor can be expressed as the square of the voltage divided by the resistance, or as the square of the current multiplied by the resistance. We now wonder how fast a carrier moves in a conductor under the action of an electric field. For this purpose, let us consider a copper wire with a diameter of 2 millimeters. In copper, the density of charge carriers is about 8.5 times 10 to the 28 carriers per cubic meter. We know that the elementary charge is about 1.6 times 10 to the minus 19 coulomb. And finally, let us suppose that the current flowing through the wire, I, is 100 milliamps. 100 milliamps is not a small current. It is not a typical current for a low power electronic application. Okay, but it's a current that can be found in some electronic circuits. We know from previous results that the current is given by the area of the section of the wire times the drift velocity of carriers under the action of the electric field times the charge carrier concentration times the elementary charge. From this last relationship, we can find the drift velocity that, remember, is the average speed of carriers in the wire. So we can find the drift velocity as the current I divided by the section area A times the carrier concentration times the elementary charge. We can now replace the symbols in this expression with their value. And what we get is that VD is equal to the current, 100 milliamps, which is 10 to the minus 1 amp, divided by the section area, which is equal to pi times half the diameter square, so 10 to the minus 6 square meter, times 1.6 times 10 to the minus 19 coulomb, which is the elementary charge, times the density of carriers in copper, which is 8.5 times 10 to the 28 per cubic meter. If you do the math, what you get is that the speed of carriers in the copper wire we are considering is about 2.3 micrometer, so 10 to the minus 6 meter per second. This result might seem counterintuitive, but remember that the current is defined as the amount of charge that goes through a section of the wire, and actually the overall amount of charge that goes through the section depends not only on the speed, but also on the amount of charge which is moving. And in a metal wire, this amount of charge moving is very, very large. So in order to get some current, you may have a large amount of charge carriers moving at a low speed.